Hello everyone and welcome back. So now that we have gone over the theory of simplex 2D noise, let's get into some implementation. So I believe we're going to break this up over two videos. We'll just find some point in which we will bring this one to a close so it doesn't run on forever. But Lee, get started.
Are you sure you just won't let me copy and paste the whole thing and
Oh no
just
no
call
no
it a day?
that's no fun.
Oh, okay, well, fine. Well, if I'm going to have to code it, we're going to need a file to hold the information in. So let's create a new item. This will be a class, and this will be our simplex noise. So here's our simplex noise. Now the nice thing is we can go to any one of these. Let's go to Perlin. And we'll copy the first part of this. Go to simplex noise. Because we are using partial classes, we can do that. So that gets our first part done. I don't need this though. Delete that and tab that. All right, so that's our initial skeleton for our simplex noise. Now we're going to have, when we're all done, two different classes in here, one for our simplex 2D and one for our simplex 3D. But we're going to start off with the 2D. We're going to keep it simple. I wish. This one's kind of complicated, but just like all of our other 2D noises, it starts off simply by taking in two floats, one for X, one for Y, and returning a float value out. So as far as that's concerned, that's not too difficult. So just so I don't get any errors for now, I'm just going to return a float out. We'll fix that at the end of the implementation. Now, all this is about is calculating out our noise contributions for our three simplex points. If you remember in the last theory video, we discussed that a simplex for a 2D space is a equilateral triangle with 3 points. Those three noise contributions will be N0, N1, and N2. And we will calculate those out, but that will actually be in the next video. We need to do some setup to figure out what those contributions are going to be before we can even calculate those. So the first thing that we need to get involved is a couple of factors to start skewing and unskewing that simplex information. Because if you remember, actually I can go back into Photoshop. If I go into our grid, this is a simplex grid. This is not the space in which we are sending information in. We are sending information in based off a rectangular grid where X and Y is in 2D rectangular space. What we need to do is start taking that information and skewing it so we can translate its coordinates into where it would be in a simplical grid. Big word, has more than 5 letters. I have difficulty with it, sorry. So, but that's what we're going to do in this first part of the implementation is we're going to handle the calculations into and out of the space and get all the information ready so we can calculate the gradient noise contributions from each of our 3 points when we get to that point. So we're just getting set up so we can figure this out later. So back into code. Let's create now this is I'm going to type it in as it appears in the paper, and then I'm going to modify it because I don't like the way they did it in the paper. I understand why they did it. A lot of the code that is in that paper was written for readability, so you can figure out what is going on and understand it better, as opposed to being optimized for speed. And this is one of those glaring points that we need to fix if we want this to run as fast as it can. What I'm referring to is we are checking for math, and we're getting the square root of the value 3, subtracting 1 from it, and then multiplying that by 0.5. From there, we're creating a new variable, which is s. That's going to be our scale factor. We're taking x plus y and multiplying that by f2. Now, square root on a modern computer with math coprocessors that are built into the chipsets and all that super fancy Wempedine stuff that we have nowadays aren't that slow, but they're not that fast either. And when we're doing 3 operations to get, in effect, what is a constant, if we were only doing this once, that wouldn't be a big deal. We're literally doing this potentially hundreds, thousands, millions of times for a single texture.
Mm-hmm.
So we don't want to do that. So we can boil down F2 and calculate it one time, and we can get a value from that, which is 0.3660254. So that is a constant value that will never change. So let's make it a constant. Oops, hit my caps lock key. And I can't spell private either. So private float const. There's a const float. I always get that mixed up. And we'll name it F2 just to keep the naming convention the same. And that will equal this value right here. See how that will never change. So now we don't need this line. But I wanted to type it out so you can see what it looks like in source code and then replace it with a constant. This, believe it or not, in I think it was the when I was doing the test with the 1024 by 1024, saved like almost 2 seconds of time. So definitely worthwhile to do that. All right, we need a couple of other variables. We're going to go with I and j again. These are going to be the floor. But instead of being the floor x like we did with the other 2 noises, this is going to be floor x plus our skew factor of s. And we're going to do the same thing with y and save that in a variable called j. And this is just skewing our information into that simplex grid format, so the information we get from there. We're going to end up with our second constant here. This is in code, it's var g2 equals float, and this is 3.0f minus the square root. I'm not going to type it all out, but it's asking for the square root of 3 again, divided by 6, which boils down to a nice constant. So we're going to turn this into another constant. And when I calculate that all out, it works out to be 2.7113249. And then we have to make another variable called t. This is our unskew factor. This will be I plus j.
I.
If. No, I like if better.
Okay.
Or is that Jif? No, that's Jif I like better. Not endorsing any brands, though. All right, so we're going to have our unskew variable of our var of t, which is I plus j times g2. So this is our unskew factor. Now let's create a couple of other variables to help unskew the information. This will be our x0, this will be I minus t. Var y0 is going to be equal to j minus t. So we're basically taking and getting the cell origin that is put back into XY space as opposed to our simplex space. Now we need to calculate how far our x and y is from that center point. So we'll have x0, little x0, equals x minus our big X0, and do the same thing with y. Now, again, the naming here is definitely kind of wonky and could probably be cleaned up, but I'm keeping it consistent with the paper for anybody who wants to compare and go through and read it so they can pretty much get a one-to-one translation back and forth of what's going out. Now, we need to figure out which simplex that we are in. So if I jump over to the Photoshop a little bit, all we've been doing is skewing from the square XY grid into the simplex grid. Now we need to determine, given the fact that we have our distance from our cell origin, which is basically right here. I don't know. Can you see my mouse? Is that moving?
Yeah, I can see it.
Let me change the V. There we go. So basically our cell origin would be the center of two simplexes.
Mm-hmm.
So we need to determine, based off of our distance from our origin, are we in this top simplex or are we in this bottom simplex? So that's what we're going to be doing now.
Okay.
And we'll create a couple of integers to hold the information for us. So it'll be I1 and J1. And a couple of conditional checks. We're going to say if x0, if x0 is greater than y0,
0.
Up. Good call. Thanks.
Mm-hmm.
I keep hitting shift while I'm doing that. If that's the case, we're in the lower triangle, so I1 is going to equal 1 and J1 equals 0. Else, it will be the reverse. So I'm just going to copy these two lines. So I1 will be 0 and J1 will be 1. So that means we're in the upper triangle. Once we've determined which triangle that we're in, we need to get some offsets for our corners and their unskewed coordinates so we can determine the noise contributions. So some more temp variables. This will be x1 equals x0 minus I1 plus our G2 constant that we created, which is our unskew or part of our unskew factor. And then var y1 is going to equal y0 minus j1 plus g2. And we need the offsets for the last corner. That's going to be for x2. That's going to equal x0 minus 1f plus 2f times g2. Control C, Control V, and we'll figure out its y component, which will be y0 minus 1 plus 2 times g2. And that will get us to the point that I wanted to cover in this video. This is basically laying in all the groundwork that we need to calculate which our three simplex corners, which gradient that we're going to be using, our hash gradients. Because if you remember, back in even in the Perlin noise, we've got these hash gradients that we're saving up, and we have the permutation tables, and we use the permutation tables to randomly choose one of these gradients. We're still doing that, so as part of the noise, which is one of the things that I've questioned, and I'm not quite sure why that's done, when you consider the fact that supposedly, well, I kind of know why it's done, and I'll go back and show, because it's kind of weird. In the paper, when you're looking at the explanation, particularly when we get to this point, and it's showing that you have a point inside, and we've got these three different gradients.
Mm-hmm.
If they were circular gradients where they're even across, that point is going to be the same every single time. There's going to be no variation in it. So if we tried to animate or had some differences in there, any point that's in here is not ever going to change. It's going to be the same value every single time, particularly if this gradient is even across from each circle. So what we're doing is we're using kind of like the Perlin noise technique, where we're randomly choosing one of those 12 directions and drawing a gradient in that direction, and then taking that contribution at that point.
I gotcha.
So we're kind of using a combination of Perlin with the simplex grid, but we're using the technique of using a randomly directed gradient, and we're also calculating in the vector to this point.
Okay.
And using that combination. And I think actually, if now I think about it, I think inside this paper he explains him doing that as well.
Okay,
Or
cool.
why he did it that way to optimize it. So, but that's the difference between what they're doing here and what we're doing in code.
Okay. Awesome.
So back to code. So ignore that. But we're getting ready to, in the next video, we're going to go through, we're going to calculate which one of those random gradients we're going to use for each of our simplex points.
Mm-hmm.
And then we're going to calculate out the contribution of the value of that gradient at our sample point. Average those together and kick those back out.
Awesome. Fantastic. All right, well, with that, that is going to wrap up Simplex 2D Noise Implementation Part 1. Thanks a lot, everyone.